So far, all of the colors that we've used in our models have come from the vertices themselves. But this is not usually how we'll render our models. Instead, we'll do texture sampling. We're going to map two-dimensional textures to the surfaces of our 3D models. So what exactly is a texture? So let me pull one up and show you. This is a texture of the Earth, and this is a 2D texture. Our texture has a coordinate system. In OpenGL, that coordinate system runs from 0, 0 in the lower left-hand corner of the texture to 1, 1 in the upper right-hand corner of the texture. Now, irrespective of what the resolution of the texture is, you'll always have those normalized coordinates between 0, 0 and 1, 1. These are texture coordinates, also known as UVs. So if you hear me talking about UVs or texture coordinates, those words are used synonymously. So let's dive right into lesson 4.1, where we're talking about textured model demos. So we're going to take the same model work that we did in the last lesson, and we're going to extend it to texture that model. The rendering game.cpp and the rendering game.h, let's look at those real quick. And notice that this looks almost identical to the last rendering game.h, but this time around, we are referencing our texture modeled demo. So we're instantiating our textured model demo, and we're deleting the texture model demo when we're done with it. And the same draw calls that includes depth buffering. So let's look at the texture model demo class. This is a drawable game component, and this time around, we don't have a vertex attribute color. Notice we still have our vertex attribute position attribute, but we don't have a color attribute. Instead, it's been replaced by a texture coordinate attribute. Now, let's look at the vertex shader to see the difference in the actual shader. So we still have a uniform mat4 for our worldview projection matrix. We still have our vec4 for position, but instead of a color, we've replaced that shader attribute with a vec2 instead of a vec4. We just have two coordinates, a u and a v. U meaning the horizontal, and v meaning the vertical coordinate to reference a specific texel within the texture. Now it's at location 1 as the color was. And notice now also that instead of our VS output structure returning a vec4 for the color, we're returning a vec2 for the texture coordinate. Otherwise, the shader itself looks very similar. We're still multiplying the position vector by the worldview projection matrix. And now we're simply passing through the texture coordinate to the output parameter texture coordinate in the VS output struct. Now, in the fragment shader has something new, and this is what I want to talk about primarily in this lesson, is the idea of sampling textures from within a shader. So notice now that we have a uniform that we've declared inside of the fragment shader. We had a uniform that we declared inside of the vertex shader. Now we also have one inside of the fragment shader. We also have a layout attribute that we've specified here for binding equals 0. That's another index, and you'll see how that's used inside of the OpenGL calls here in just a moment. This one is type text sampler 2D. Now, a texture sampler is what we'll use to actually get colors out of the texture. But textures can actually be used for lots of different things. We can store normal data inside of the texture. We can store height information, height map data, if you've ever heard of that term. But we're going to be using this primarily in these lessons here for color. Notice that the VS output struct as input this time around. So VS output from the vertex shader, but VS input, if you like, into the fragment shader. And there's our texture coordinate. Now, we still output a vec4 for color, but this time, instead of that color coming from the color of the vertex, we sample the color, and we do that with the texture intrinsic. Now, the texture intrinsic has two arguments. The first is the color texture sampler 2D object. So we're going to specify our sampler 2D object as the first argument, and then the second argument to the texture method is the input texture coordinate. Now let's hop over to the actual texture model demo. And let's see, we're still creating our vertex buffer from a mesh. We still have similar keyboard handling. We have a shader program. We still have our vertex array objects, vertex buffers, and index buffers. This starts to repeat itself after a while. These are the common patterns that we're laying down with this framework. We still have our worldview projection location and world matrix, our index count, but now we have a couple of new things. We've got a color texture, and I've also declared an alternate texture so we can swap between textures. And then we have an active texture, which is which of these two textures is active. And we'll be able to toggle those with a keyboard handler. Inside of the texture model demo implementation, let's hop over there now. Let's look at the initialize method. And inside of the initialize method, we're compiling and linking our texture model demo vertex and fragment shaders. We're loading that same sphere object that we loaded the last time around. This time we're actually going to map it with a texture. Just as before, we have the same concept of creating a vertex buffer out of the mesh, but our create vertex buffer method is a little different. Instead of creating a random color or a fixed color or getting the color at all from the mesh, Instead, we're getting the color from the mesh's texture coordinate. So we're not using the color that comes from the mesh at all. Instead, our vertex position texture objects, this is a different type of object now that we're pushing back into our list of vertices, is populated by the position of the vector and the UV, the texture coordinates for that particular mesh. So let's take a look at vertex position texture. This matches the vec4 and vec2 inputs into our vertex shader. And that's it. Vertex position texture, just to denote that it's got both a position and texture coordinates. Continuing with the initialize method, we find the location of our worldview projection location. Now we start loading the texture itself. In fact, we're going to load two different textures. This is the first time that you've seen the simple open image library in action. So soil load OGL texture. What that call does is it loads a variety of formats. JPEG and PNG are two examples here. It also loads Targa formats, TGA files. And there's a few arguments that you use in order to reference that method. Soil load auto, create new ID. You can look up a little bit more information about the soil load OGL texture on their online documentation, but these are very common arguments, the defaults, if you will. This next argument needs a bit of explanation. Soil flag MIP maps. We're going to talk about MIP maps here in just a moment. In just a couple of lectures, we'll talk about MIP mapping. But the idea of MIP mapping is we're going to, on the fly, generate smaller versions of the input texture. So if we look at this texture again, it has a resolution of 2048 by 1024 pixels. So 2048 by 1024 pixels. But MIP maps, when we generate MIP maps, we can make smaller and smaller and smaller versions of that texture by a factor of 2, all the way down to a 1:1 texture. I'll explain where they're used in just a moment. But for right now, just know that that flag is generating MIP maps for this texture. If the soil load OGL texture fails, we'll throw an exception. And likewise, we'll throw an exception if we fail to load the checkerboard.png file. Let me pull that up here and I'll show you what that looks like. So that's just checkerboard.png. And notice that it's a smaller texture, but that's okay. And we're going to specify the active texture to our primary color texture. And again, the active texture and color texture, this is just so that I can swap between these two in a simple demonstration that we can use the very same source code, very same draw calls, but swapping different textures out. Similarly to the last code that we looked at, we build up our vertex array object by binding the vertex array object to the OpenGL context, and then by setting up GLVertex attribute pointers to the position and texture coordinate members of the vertex shader. Now notice this time around, instead of specifying 4 elements for our texture coordinate vertex attribute, we're just specifying 2, because that's all it is. It's a U and a V. And these are GL floats, and likewise as before, these are false. We're already going to pass them in normalized. They'll already be between 0 and 1. And this time the offset of is to the texture coordinates member of the vertex position texture struct. This is the first time that we've actually used the keyboard handler within a game component, so let's explore this a little bit. This is a keyboard handler that is specific to this component. Remember I had mentioned back in the game class that you can stack, you can have multiple keyboard handlers. So even though the rendering game class also has a handler, so does the texture model demo component. Now this key handler does something a little different. If you press the space key, then I'm toggling the active texture. So finally we come to the draw method. And inside of the draw method, we do our typical calls for binding the vertex array object, associating the vertex buffer with the GL array buffer target, and the index buffer to the GL element array buffer target. And now we're going to call GL bind texture to take whatever our active texture is at the time. Remember that could be changed by the spacebar press. So we're going to take our active texture and bind it to the target GL texture 2D. Now that GL texture 2D, there's actually can be multiple textures mapped to the pipeline at any given time, but right now we're just going to map one, and the target that we care about is the GL texture 2D target. We're going to use that shader program that we had previously compiled. Remember, this is a different shader. These are our texture model demo fragment and vertex shaders. In this case, the worldview projection matrix, we haven't modified it. We're not spinning the object that we were looking. We could, of course, we could spin the object and make the world go round. We enable backface calling and specify the counterclockwise for front-facing triangles. And then we call GL draw elements and we pass in the index count. And we specify that those indices are of type unsigned int. Very similar calls as before. The major difference here is now that we're binding the active texture to the GL texture 2D target. So now let's run this and see what happens. We have the same sphere that we did in the last demo. This time, instead of that sphere having random set of colors or having a fixed color, if we specified every vertex to have the same color, now we're sampling those colors from the texture. And that's all done with that simple GLSL texture call. We specify a sampler, a 2D sampler. We specify the input texture, the active texture that we're going to pass in. And now I'll notice that if I just press the space bar, I can toggle between the active textures. Without reloading, without changing our draw calls at all, we're just toggling between textures there. So that ends our first look at texture mapping in OpenGL.